In this video, we're going to talk about the product rule. We're going to talk about how to differentiate a product of two functions. So how do we differentiate y equals f of x times g of x? For instance, x squared times sine x. Well, if the two functions were added instead of multiplied, we would just differentiate the two functions and add the results. So you might be thinking, well, shouldn't we just differentiate these two functions and multiply the results? So is the derivative of x squared sine x 2x cosine x? Well, let's try a simpler example to show why this isn't the case. Let's look at the function x cubed times x to the 7th. You know how to simplify this function, but for now let's just pretend that we don't know how to simplify it and we're going to differentiate it. Well, if you use the conjecture above that you just differentiate the two functions and then multiply the results together, you would get as the derivative 3x to the 2nd times 7x to the 6th, and I'm going to put a question mark over that equal sign because, well, we don't know that it's true yet. And that would be, what, 21x to the 8th. However, we know what the answer really is. We do know that y is equal to x to the 10th, and so y prime is going to be 10x to the 9th, which is not the same thing as 21x to the 8th. So the product rule, sometimes known as Leibniz rule for the discoverer, if y is the following: if y equals f of x times g of x, then y prime equals f of x times g prime of x plus f prime of x times g of x, provided that f prime of x and g prime of x both exist. Sometimes I will write this way: if y equals ab, then y prime equals ab prime plus ba prime rather. Let me say a little bit about order. The derivative, the formula for the derivative, consists of expressions which are multiplied together or added, and multiplication and addition are each of those operations is commutative. So the order here is completely flexible. Alright, so let's try differentiating x squared sine x. So I'm going to call x squared a, and I'm going to call sine x b. So the derivative would be a b prime plus b a prime. And that's going to give us x squared times cosine x plus sine x times 2x. And I'm going to take out a common factor of x in these two terms, and that's going to leave us x cosine x plus 2 sine x. Very often when we get a derivative, we're going to need to do things like set it equal to 0, and so being able to factor these things and actually getting in the practice of factoring the derivative is not a bad idea. Also, this product rule can be extended to a product of 3 or any finite number of functions. In the case where y equals a times b times c, y prime would be equal to a b c prime plus a b prime c plus a prime b c. I hope you see the pattern there. Alright, so let's differentiate this example. Y equals x squared sine x cosine x using the rule. So x squared I'm going to call a, sine x is b, and cosine x is c. So y prime is a b c prime plus a b prime c plus A prime BC. We're going to get x squared times sine x times negative sine x plus x squared times cosine x plus 2x sine x cosine x. Ran out of room there, sorry about that. Or to neaten this up a little bit, let's call it negative x squared sine squared x plus x squared cosine squared x plus 2x sine x cosine x. There is a common factor of x in all three terms, so factoring that x out would be a good idea, perhaps.